Okay, so we are starting the next unit on electrochemistry. Now, one thing I need to correct, I really apologize for this, on all the videos when I converted 8.314 joules, remember that's our R, to kilojoules. I know it's divided by 1,000, but I added a 0 in there. It goes to show you, this is a great example of how sometimes it's better just to punch it in your calculator than move the decimal over, because if you do it wrong, then... So all of that, I think I put in some of the videos 0.0008314. The actual answers to the problems are correct. So you don't need to go back and change those. Just make note that I did that wrong. Okay. Now, what we're going to be looking at in this unit is electrochemistry. We're going to look at basically the equations of a pair of equations, one of which oxidation is occurring and one in which reduction is occurring, and we're going to put them together. And a lot of this is going to be look familiar to you. We're going to create an electrical current because as one element gives to another its electrons, those electrons flow through a wire, and that completes an electrical circuit, much like what you'd see in a battery. But before we do that, we've got to get straight when something is being oxidized and when something is being reduced. Because if you get that backwards, you'll get the whole unit will be wrong. It's sort of like delta G. If you don't remember that negative is favorable, everything kind of falls apart from there. Okay. So this is all review. We did this in another unit. I can't remember which one, but you've seen all this before. We have this mnemonic device, that's oil rig. Oxidation involves the loss of electrons, and reduction involves the gain. And I always remember this one becomes more positive, and this one becomes more negative. Now remember, if we need to, we can use our number line, where oxidation is this side, we have 0, and reduction is this side, because sometimes reduction will occur from +4 to +2. It's easy from 0 to -2. Most students are like, yeah, that's reduction, I can see that. So if you need to use the number line, you can do that. Now, let's write a balanced net ionic equation for the reaction between zinc metal and aqueous hydrochloric acid. Oh, this is a great time. I'm going to do this here. I'm going to review the net ionic equations with you. All right. So remember, when we write a net ionic equation, we write the complete balanced chemical equation. So if I'm reacting zinc with hydrochloric acid, then I get zinc chloride and hydrogen gas. Okay, now remember, we drop all of this in water. Zinc isn't going to do anything, so it stays like this. This is a strong acid, so I'm going to get H+. Oh, actually, I need to balance this. There should be a 2 there. So I've got 2 chlorines and 2 hydrogens. So I've got 2 of those and 2 Cl-, right? So that's all, because those are strongs. They completely dissociate. This is an ionic salt, so it's going to dissolve in water. Right? And then H2, that is a covalent bond. We are going to keep that exactly how it is. It's not going to dissolve in water. All right, we go and we look, and that's going to go away, and that's going to go away. So we have this. Zinc plus H2 gives zinc 2+ plus hydrogen gas. Right? So remember, we do balanced, complete, net. So zinc solid plus 2 hydrogens give zinc 2+ plus hydrogen gas. Okay. Now, in this reaction that I wrote, remember who is losing and who is gaining. Zinc is becoming more positive. Remember what we're losing. We're losing electrons. Electrons are negative. So if I'm losing negative things, I become more positive. So it's being oxidized. Hydrogen is more positive. It's here. So zinc is going from 0 to 2. That's oxidation. Hydrogen, however, is going from +1 to 0. That's in the reduction direction. So it's gaining electrons, and therefore it's being reduced. Okay. Now, this is a review for you. If you want to go back and kind of look at all of these and check them, you can do that. But you need to be able to look at these chemical formulas within these chemical equations and know what elements are being oxidized and what are being reduced. And so I'm going to do a few of them with you. Remember some of the rules. Elements are 0. Halogens are usually -1. Hydrogen is usually +1. And oxygen is usually -2. Not always, but usually. So start with those elements and then kind of work from there. So halogens are usually -1, but I've got 3 of them. So this is a -3. So phosphorus has to be a +3. I've got 1. This is a -2. So that means this has to be a +2, but I've got 2 of them. Therefore, of course, it's a +1. And notice I don't care about the coefficient. That means nothing. I can have 1,000 of them. The oxidation states of the elements are within the compound. We don't care how many we have. Let's look at this one. It'll be a little trickier. I always like to go for the oxygens first. I've got 3 of these. They're worth -2 each. That gives me a -6. That means all of this on this side has got to be a +6. I've got 3 +1s. So that means phosphorus has to be a +3. And now both sides are neutral. This is an easy one, -1 +1. Let's go down here. Remember, hydrogen is a +1 times 3 is +3. Then phosphorus needs to be a -3. Oxygen is a diatomic. That's an element. That is 0. Okay. And so now we've got oxygen here is a -2. I've got 5 of them. That means I have -10 on this side. So I've got to be a +10 here, but I have 2 of them. So each of my phosphorus are a +5. All right, we'll look at water. This is a -2, and I've got 2. Each of these is a +1, and that balances. Okay, now why do we want to do this? Well, in each of these reactions, well, not all reactions, but if it's a redox reaction, we're going to have some of the elements changing their oxidation state. Now, if I look in this one, +3, +3, -1, -1, +1, +1. This is not a redox reaction because nothing is changing in its state. This next one, however, is different. Look what's happened here. In this one, my phosphorus is going from a -3 to a +5. It's being oxidized. And my oxygen is going from a 0 to a -2. That is being reduced. So that is an oxidation reduction reaction. Right? So that's what I want you to be able to do. You can work on the next 2 and see if you are able to determine whether or not these are oxidation. This is not a redox. So this is redox. And this is redox. See if you can figure out how I figured out that those two are like that. Okay.